Hi everyone. Instead of the normal review session that we do on Monday afternoons, we decided to do this review session a little bit early, but we're going to do it obviously digitally, just so you would have some idea over the weekend of what you're doing for your final project. The point of what Tim and I are going to do right now is not to give you every detail of how to perform the entire project in each section, but we do want to go through essentially each section of the experiment of the project and give you a general idea of how you might get started. So please don't expect to find every single detail, but at the same time you are going to find some hopefully some useful information. Because there are a very large number of people taking general chemistry, it's very challenging for us to respond to emails where we go into lengthy explanations. And plus it's hard to make lengthy explanations by email. So if you have questions, please stop by office hours. You can find TA and staff office hours listed on Blackboard, and we're more than happy to help you out in any way that we can. It's just more efficient for you and for us if you come and see us, and we can help you. So now let's get right down to it. So the first thing, one of the first things you're gonna have to do is spectroscopy. So maybe this is your section. And for the spectroscopy section, you essentially have a yellow food coloring, whether it's yellow 5 or yellow 6. And the food coloring that you're going to be given as a stock solution is 2.0 times 10 to the minus 3 molar food coloring. And it's probably yellow, 5 or 6. So you have this food coloring at this concentration. Your goal is to determine the concentration of food coloring in the unknown solution to see if they have violated the copyright law and are copying someone else's solution. So how you're going to do that is, just like you did in the general chemistry lab earlier, you're going to make a calibration curve. On one axis, you're going to have concentration, and on the other axis, you're going to have absorbance. And these absorbances should be between 0.1 to 1.0, approximately. If you have something that's 1.1, that's probably fine, or 0.9 or 0.93, that's probably fine, but approximately 0.01 to 1. And you want to have on this calibration curve 5 points. Now, as I mentioned earlier, the point of this video is not to tell you exactly how to do this. In fact, we're not going to tell you exactly how to do this, but we do want to give you some idea. So one place that you might start is figuring out what concentrations of the food coloring will give you an absorbance of 0.1 to 1. And you could do this by looking up the molar absorptivity coefficient and using A equals EBC and calculating that. But I'm going to give you more of an empirical way. And the reason the empirical way, or research-based way, is important is because these food colorings are not always pure. So sometimes the molar absorptivity coefficient you look up doesn't correspond to what's actually in the sample that we use to make the 2 times 10 to the minus 3 molar solution. So what I suggest you do is make a series of solutions. Say 2 times 10 to the minus 4 molar, and then 2 times 10 to the minus 5 molar, so on and so on and so on, diluting by 10 each time, minus 5, minus 6 if you need it, by simply taking 1 ml of 2 times 10 to the minus 3 molar and 9 mLs of water. You could repeat by taking 1 milliliter of this and 9 milliliters of water to make this. If you want to make it 1 order of magnitude smaller, you could repeat again. Each of these times, measure the absorbance of these solutions. Remember to blank the spectrophotometer, measure the absorbance, find lambda max, and look for something that's between 0.1 and 1. Now, as an example, and this is not a true example, it's just an example, if, for example, you found that 2 times 10 to the minus 7 molar food coloring gives you an absorbance of 0.73 AU. This would be some information that you could obtain by empirically determining what concentrations you should use here to give you absorbances between 0.1 and 1. Well, what you would want to do is a proportionality to figure out which one will give you, what concentration will give you an absorbance of 1. And to do that, all you have to do is take 0.73 is to 2 times 10 to the minus 7 as 1, the absorbance that you want, is to X, the concentration that you want. And what you're going to find is that X equals 2.74 times 10 to the minus 7 molar. This would tell you, and again, these are made up and this is not correct, this would tell you that if you want to have an absorbance of 1, you need to make 2.74 times 10 to the minus 7 molar. So here you'd have 2.74 times 10 to the minus 7 for your concentration, and your absorbance should be around 1.0. You'd have a point. Now, what you would then do is figure out where you'd have an absorbance of, say, 0.8 or 0.6 or 0.4 or whatever the case may be, dilute up, make all of those solutions, and make your calibration curve. Finally, make your unknown and compare the equation of your line to the absorbance of your unknown to find the concentration of the yellow food coloring. The next thing that you may have as your section is conductivity. So I do want to talk about conductivity as well, and then I'm going to turn it over to Tim. So with the conductivity, we're trying to find the conductivity of the sodium citrate solution. So we have sodium citrate. And we're going to need to make a stock solution of sodium citrate. This is a solid, so this is not a solution like the yellow food coloring. And our goal is exactly the same thing. We're going to make a calibration curve where we have concentration on this axis, and we have conductivity on the y-axis. And in this case, our conductivities must be between 300 to 6,000 centimeters to the minus 1. So these are our, this is microsiemens per centimeter to the minus 1. So these are your conductivity ranges based on your concentration ranges. But again, you're in the same position where who knows what concentration of sodium citrate is going to give us these values. And here it's even more challenging because you're probably not going to be able to look this up like you could look up a molar absorptivity coefficient. So what we suggest you do is you start with 100 milliliters of 0.05 molar sodium citrate. And a couple things to point out here. One, we're not going to tell you how to make this. Second, you're going to have many more decimal places than this, right? This does not have the right number of sig figs. With our balances and our volume measuring devices, you can certainly get better, more sig figs than this has here. But you want around 100 milliliters of 0.05 molar. You're not required to do this, but this is where I would start. Again, once you have this, measure the conductivity. So let's say you would start with 0.05 molar. Measure the conductivity. Then you would dilute it 1 in 10, 0.005 molar. Measure the conductivity. To make this, you take 1 milliliter of the 0.05 and 9 milliliters of water. So you could dilute it by 10. Repeat until you get a conductivity between 300 and 6,000. So here, again, I'm making up these numbers, but let's say, for example, that you took 5 times 10 to the minus 6 molar sodium citrate, and it gave you a conductivity of 2,100 microsiemens per centimeter. So this is basically the concentration that you find by diluting this by 10 many times until you get 10 to the minus 6. And this is the conductivity you find, which is on your range of 300 to 6,000. You're going to do the exact same thing that you would do for the absorbance. You're going to take that 2,100 is to 5 times 10 to the minus 6 molar, that's a 6, as 6,000, the top of your conductivity range, is to X. And in this case, you'd find that X equals 1.43 times 10 to the minus 5 molar. Now you have to figure out how do you make your original 0.05 molar stock solution into this concentration. Just like before, your concentration will be 1.43 times 10 to the minus 5 molar. Your conductivity will be 6,000. Then you need to dilute it to maybe make a 4,000 and a 2,000 or a 3,000 or whatever you think is appropriate so that you get 5 points over a range. You then measure the conductivity of your unknown, use the equation of the line, and you can find the conductivity of the unknown. Again, note, I just want to point out, in both the absorbance case, or excuse me, the spectroscopy case and the conductivity case, these numbers that we made up to do these example proportionalities are not necessarily correct. We just made them up to give you an example. I'm going to turn it over to Tim now, who's going to talk you through the other two parts of the experiment.
All right, so another potential portion of the experiment that you could have is freezing point depression, where you have to determine how much the solution depresses the freezing point of water. This portion of the experiment is very, very similar to what you performed in experiment 13. So if you need extra help figuring out this section, I strongly suggest that you look at experiment 13 from your lab manual this semester. For each of these sections of the experiment, you have actually done something very similar or exactly the same in lab, and you can find those in your lab manuals. We strongly recommend that you use those resources to help you in this experiment. So for the freezing point depression, what you're going to do is you're going to take and freeze 5 grams of your solution. This is the unknown solution found in the hood provided by me. And you're going to freeze 5 grams of it 3 times. And you're going to do this the exact same way you did in experiment 13, like I said before. You're going to make an ice salt bath in order to freeze this solution. And again, just like in experiment 13, be sure to use plenty of salt. Do not be afraid to use additional salt to make your ice salt bath. If you don't use enough salt, you're never going to get your solution cold enough to freeze the unknown. So you're going to make it with plenty of salt, and then you're going to make sure that while it's freezing, you stir continuously. These two parts are very important. You need to use plenty of salt, and you need to stir continuously. If you don't do these things, then the experiment will not work correctly, and you'll be unable to complete this section of the experiment. Once you've done this, you're going to use the microlab the entire time. In fact, you're going to use the microlab to measure the freezing point. Be sure to account for supercooling. So make sure that you measure the freezing point after supercooling occurs. When you're doing this experiment, remember that on your graph of time versus temperature, you're going to see the temperature coming down over time, and then you'll see one of two things. If you have supercooling that occurs, you'll see the freezing or the temperature of the solution jump back up, and this area here is your supercooling, and up here is your actual freezing point, and down here is the solution not reaching a fully frozen state yet. So make sure you don't record this temperature and use the correct freezing point. Like I said, this is very similar to experiment 13, so be sure to use that resource to help you with this portion of the experiment. The final section of the experiment is titration. You're going to determine the pH of the solution using the Henderson-Hasselbalch equation. We've decided to make you use the Henderson-Hasselbalch equation because this reaction, or rather the solution, contains both an acid and its conjugate base. And as you know, the Henderson-Hasselbalch equation says that the pH is equal to the pKa plus the concentration of the conjugate base, which in this case is citrate, divided by the concentration of the citric acid, which is, again, our conjugate base divided by the concentration of our acid. So you're going to have to find the concentration of your citric acid. Sorry, I forgot to include the log of your citrate divided by your citric acid. That is important, and without it, you would not get the right answer. So we have a few things we need to talk about here. This is exactly the same thing you did in lab this past week with acetic acid, but instead we're doing it with citric acid. So make sure you follow what we did last week. If you need to, you can find a video going over experiment 17 on YouTube on our channel that will go into more detail on that experiment. So this time around, we're again going to need to standardize some NaOH. And I'm not going to go into excruciating detail on how to do this because you did it last week, and the other video can be found online. And again, we kind of don't want to give you the exact rules of how to do things in the project. We just want to give you some guidelines to get you started. So you're going to standardize your NaOH, and you're going to have approximately 0.1 molar NaOH that you're going to use from the stock 5 molar solution in lab. And to standardize this, you're going to standardize it using, just like last week, approximately 0.2 grams of KHP. This will help you determine the exact concentration of your NaOH. Once you find the exact concentration of your NaOH, you can titrate your solution to find the concentration of your citric acid. Once you have found the concentration of the citric acid, we can plug it back into our Henderson-Hasselbalch equation. However, there's another variable in the Henderson-Hasselbalch equation, the concentration of the citrate. This value you will get from the conductivity portion of the experiment. So you're going to need a value from one of your other group members in order to finish this portion of the experiment. It's important to note that you do not have to wait for them to finish to perform all of the lab work that you're doing. You can do everything except substitute your variables into this equation before they are done, and then once they're done, you can substitute in your conductivity value. The only other thing you need to plug in is the pKa. Citric acid has 3 pKa values that you can find in the literature, and you should use the third or highest pKa value for citric acid, as this is most closely the pKa of the citric acid solution. So make sure that you use the third and highest pKa value when you substitute in. Now you'll have a pKa, a concentration of your citrate, and a concentration of your citric acid, and you can determine the pH. You'll then want to compare the pH from the Henderson-Hasselbalch equation to the actual pH. And this is just to ensure that your methodology of using the Henderson-Hasselbalch equation worked correctly. To find the actual pH, you're going to just use a pH probe. And that will give you the actual pH of your solution. So once you've done all of this, you're going to then need to finish up the experiment. So you're going to need a conclusion to your experiment. In this conclusion, you're going to have measured 4 things. You're going to find the concentration of your dye, you're going to find the concentration of your citrate, you're going to find the freezing point, and you're going to find the pH. These 4 values will then be compared to the values in the lab handout that you can find on Blackboard. So you're going to compare them to the values in the lab handout for your assigned solution. Be sure that you're comparing them to the correct solution, otherwise things are not going to work out right. And you're going to need to compare the concentration of your dye to the listed concentration, the citrate, the freezing point, and the pH to all those things and find out, was the recipe stolen? It's really important that you include this portion of the work in your final lab report and in your presentation that you're going to give, because this is very important, or this is the whole point of the experiment. While it is important to learn the skills and practice the skills that you're going to be doing in the experiment, the application of those works is also the point of the experiment. So I want to leave you with just one more thing, a little food for thought, if you will, before we leave you to do your project next week. And I just want to ask you to please consider how mixtures may affect individual properties in a solution. In this experiment, you're going to be measuring the conductivity of a system that does not include only the salt of interest. It's also going to contain dye, and it's also going to contain acid. The same holds true for each of the other portions of the experiment. So we want you to remember to keep in mind that those things may have an effect, and if they do, what kind of effect could they have? As Colin said at the beginning of this video, if you have any further questions, please see him, I, any other staff member, or any of the TAs at office hours to seek the help that you need. It's really important that you're ready to go when you come into lab on Monday, because you only have approximately 2 lab periods to do this, so it's important that you're ready when you show up. As an additional reminder, keep in mind that you're not going to be doing these sections one time each. You're going to be measuring each of these values in triplicate. When we say you're going to measure the values in triplicate, I don't just mean you're going to measure your unknown dye 3 times. I mean you're going to make 3 calibration curves of dye. You're going to make 3 calibration curves for your citrate. You're going to do your entire titration 3 times, and you're going to measure the freezing point 3 times. It's a lot of work, so it's really important that when you come into lab next week, you have a plan for how you're going to tackle that work. That said, again, please come see us in person if you need additional help. As Colin said, there are simply too many people, and it is too difficult to try to explain complicated chemistry through email. So coming in person will make it much easier for us to help you with the experiment, so we strongly encourage that. That said, that's all we have for you, and good luck on your project next week.